Well, hello everybody. How's it going? This is Ali with the AI Enthusiast, and today we're going to be talking about self-attention versus cross-attention. And you might be wondering why. Well, first off, it's a very important topic. If you understand this, I really do think you're going to understand like one of the core parts of the transformer architecture. And also like it's a point of confusion. So I want to go over this today, and I'm going to go over at a high level conceptually what's going on, and then we're going to also code it up. So as you're coding, as I'm coding, I want you guys to follow along if you can, so that you can actually practice and get familiar coding up these mechanisms. And without further ado, let's jump right into it. All right. So looking at the screen, we have the attention is all you need paper, and on the left-hand side you have the encoder. On the right-hand side you have the decoder, and so today, in this video, we're going to be talking about specifically the attention mechanism, the self-attention mechanism in the encoder, and then also the cross-attention mechanism in the decoder. We will not be talking about the masked multi-head attention. We can talk about that in a separate video. Just let me know in the comments, and I will happily make a video on that. Also, with multi-head versus single head attention, we're going to be just focusing on single head attention today. And the reason for that, guys, is because, if you understand single head attention, the leap to multi head attention isn't significant. So I really just want to focus on the key parts today. And yeah, so let's actually, the key thing here now, then going into self-attention, the single head here, and then the cross-attention here are these arrows. So this is a little confusing. I do like to use Sebastian Roska whenever I get a chance, and I'll put the links in the description. But over here, you can see in this article, he's unrolled these encoder-decoder blocks. So this is block notation, and you can see here n equals 6. So you have 6 encoders here. And the last encoder, that's actually the output of this last encoder is what's fed into the decoder. And all of them, each and every one of the decoders takes this input. The really cool thing here is it's easier to visualize what's going on. So let's look at the encoder block. The encoder block itself, it's basically taking in a sequence of embeddings, right? And then so let's just say our context window or our number of embeddings is 100. So you have 100 embeddings, and then your embedding is it's a vector. So let's say the vector size is 10. So you have 100 by 10. That's your matrix, and that's being propagated from one encoder to the next. Each encoder is just spitting out 100 by 10, right? So 100 embeddings, each embedding is 10 dimensions. And so then the last encoder spits out the same matrix. And then from there, that's going to be propagated through to each of the decoders. And so specifically, we're talking about this arrow here that's flowing in, multi-head attention. Now, what's exactly going on here? So with single or self-attention, we have the K, V, and then the Q. So what's going on is we have a K matrix, a K weight matrix, and we have a V weight matrix. We're basically computing the key and the value tensor off of what the encoder generated, the last encoder. And so that is the key insight. And then basically, inside of the decoder, you also have, out of this masked multi-head attention, you're going to have a sequence of embeddings. Let's just say 100 by 10. It's going to be the same, right? So you have 100 by 10, and that's going to feed into your multi-head attention. Now, that is the decoder embeddings. So you have the encoder embeddings, what the last encoder generated, and then the decoder embedding. And for that, you're gonna have the Q matrix, so the Q weight matrix. And I think this is a lot easier to understand with this article here. In particular, if you scroll all the way down, you can visually see what's going on in this nice little diagram here. So this is just a self-attention mechanism where you have your number of tokens. We were talking about 100. Our embedding size was 10 for D, right? And then we have 3 matrices. You have your WQ, which is your Q matrix, the queries, WK, key matrix, and V for values. And so you multiply this out. So you have an N by D and, basically a D by DQ. So so you'll see, we'll keep this simple here. You have the weight matrix, whatever this is, it's going to multiply. This is D dimension, this is D dimension. So you're going to get with N by DQ. And, you know, likewise, it's going to be the same for the K matrix. You're going to get an N by DQ. And then finally, for the V matrix, WV, you multiply, you get an N by DV. For simplicity, we can just say that DQ and DV are the same. You know, the point is, you have all three of these weight matrices for self-attention, right? For this encoder block here, this block here, the multi-head attention, again, we're just talking about single head. This self-attention block, what's going on is exactly what we're seeing here. We're taking the input and then we're generating these three intermediate matrices, these tensors, and then from there, it's your regular operations for attention. So you have QK, you're going to take the transpose of 1, then you get an N by N attention matrix. You're going to softmax it. You're also going to, scale it. So scale the numbers down by the square root of the, the dimensions of the attention. And then from there, you're going to multiply that out by your V matrix. So you have an N by N times an N by DV, you're going to get an N by DV output. So that is what's going on in the self-attention. The key thing there is from a cross-attention perspective then is notice how you have two input sequences. So like I said earlier, the encoder is generating its own sequence of embeddings. And that is being fed in to as an input. That's your first sequence. And then your second sequence is just your, coming internally from your decoder block here in your masked multi-head attention. This is spitting out, just like this multi-head attention, all it's doing is spitting out the same number of embeddings. So if you had 100, which is the number of tokens or your context window, so then you have 100 times your embedding dimension by 10. So you have 100 by 10 coming inside here, and then you have the encoder's embeddings coming in from the multi-head attention here. And so once you have these two sequences, the key here is then the query matrix is going to go with your basically your decoder sequence. And then your K and your V matrices, they're going to operate on your encoder. Okay, your actual encoder sequence. And, there are some subtleties here, but the key thing to realize, guys, is N by M, right? So the encoder, right, that list of, that 100 by 10 tensor we were talking about, the number of tokens of the encoder, it doesn't have to be the number of tokens that you have in your decoder. And that's a critical insight. So this is very important actually from if you're talking about using like a vision encoder. So you basically have a vision encoder that may not have the same number of embeddings. So your N might be different from your decoder that you plug it into. So all I mean to say here, or the key takeaway here, is your encoder, it's going to spit out a list of embedding vectors. That list doesn't have to be the same size as the list of tokens your decoder is using. So like when you feed this in autoregressive fashion, it's generating text. You do not need to have the same context window here and versus like the N blocks, or N tokens or embeddings that you generate from the encoder. So now once you do that, it's generally the same process. So now at this point, I'm going to stop and I'm going to go into the coding side of things, how we actually code up the self-attention versus the cross-attention. And if you guys have any questions conceptually on what's going on, let me know. But yeah, let's get started.